So hello, let's get into it. We've been talking about waves, and we did with I put away my ukulele. I should have kept that out. We did waves on a string, which I demonstrated with my little ukulele, my out of tune ukulele. And we talked a little bit about light waves, electromagnetic waves, which just move at the speed of light. But today, we're going to move in and talk about sound waves. See, when I did the ukulele, I talked about how different frequencies we hear as different pitches. But the idea is that I was just working at the frequency of the spring bouncing back and forth. That was just the movement of the spring. That was not how the wave is coming from the speakers in front of you to you, or your headphones to you, depending on which one you're using. And here's the general idea. Sound waves are longitudinal waves through metal. What it is that what happens is my throat has pieces in it that vibrate. And when it vibrates, it's going to vibrate the air. And the air molecules vibrating is what sound is. That these air molecules vibrating travels from my mouth to this speaker, to this microphone. Then a whole bunch of digital shit happens that we're going to ignore for now. And then wherever you are, that the speaker is going to vibrate the air molecules, and that is going to vibrate the air molecules and pass through. That's the idea that in space no one can hear you scream. There's no sound in space. In space, it'll be completely silent because you cannot have sound without a medium to travel through, and it has to be a medium that can vibrate. Sound does not travel well in water because water can't vibrate as easily or compress as easily as air. But yeah, that's what a sound wave is. It's the vibration of molecules. It's actually the whole reason why helium, if you suck helium gas, your voice goes high pitched. It's because it's just changing the when you change what the gas is, you start changing what frequency you vibrate things at. Now, sound waves, as I said, are longitudinal waves. A tuning fork, how a tuning fork works is when I forgot to grab something to hit it with. When you hit a tuning fork, what happens is these prongs start vibrating back and forth. And they just kind of go woo, 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 woo. And as they go woo, 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 they're going to cause the air on either side to compress and stretch out. Well, basically, we're taking the air molecules and shoving it close together and then having it stretch out. And then shoving it close together, then having it stretch out. With the areas that are stretched out called rarefacted. It is compression and rarefaction. Because every time the tuning fork, let's say my air is sound's going this way, if the tuning fork goes that way, it's going to compress the air molecules. When it comes back, it's going to let them separate. It's basically going to be as if I had this piece here. Let me use my shirt as a backdrop, it'll show up better. And I just start pushing this back and forth one side. That's what hitting the tuning fork is doing. Is it's causing the air molecules to get close together, fall apart, close together, fall apart, as these forks are just kind of going. That is what's happening here. That'll work. And so when I hit this, I get that noise, which is probably pretty loud to you guys. I'm sorry, that's a really loud tuning fork. Let's use this one. Because what's happening is they're just bouncing back and forth. Make sense so far? I actually already kind of already said all this. That when you hit a tuning fork, the fork sways back and forth, the compressed air in front of it as it moves forward. When it moves back, it has an area that's less compressed. I already said that. In fact, a guitar string really is the same thing. When you push it back and forth, it's just causing the air molecules to get compressed and rarefacted back and forth quickly. Now, as long as some sound is produced, this compression rarefaction will continue through the air, making a wave. And this is like a little GIF of what kind of sound waves are. Like, let's say this is the air molecules. What it is the air molecules don't really move. Like, if you're right up against someone speaking, you can feel the air in your hand, but that's just the force of the air leaving. But like, if I go This is so much makes more sense when we're in person. But if we were in a classroom and I was talking in the front of the class to you, the air from my mouth would not be coming from my lungs and hitting you. It doesn't travel that far. It travels about 6 feet. That's the whole reason for social distancing. What it is the wave travels that far. The areas of compression and rarefaction travel that far. Take a look at the GIF below. If you look at these red dots, as the sound wave travels, because sound is a traveling wave, and you can see it's traveling to the right. The red dots do not make their way to the right of this GIF. They kind of stay mostly in place, just kind of bouncing back and forth a little bit. But the wave travels, the areas of compression, the areas of rarefaction. And basically, what happens when these vibrations hit our ear, we evolved in such a way that when those vibrations hit our ear, our brain can interpret it as sound. The frequency of this wave we do as pitch. I talked about this last time, but like this is a 426 hertz frequency. This right here is a 288 hertz frequency. Different pitches, different frequencies. Any questions though? Now, when we talked about light, we had the electromagnetic spectrum, right? That electromagnetic rays had visible light and gamma rays and microwaves and X-rays and infrared and UV. Likewise, we can look at the sound spectrum. Sound waves fit into 3 categories. This is the sound spectrum. The 3 categories are infrasonic, audible, and ultrasonic. The short version is, this is based off frequency, just like the light was based off frequency. This is not volume. Humans can only hear a certain range of frequencies. We, as people, can hear things between 20 hertz and 20,000 hertz. About. Side note, that isn't really set. Everyone is slightly different for what frequencies they can pick up, and it also changes as you age. The older you get, the worse you are at picking high-pitched frequencies. It's just a fact of life. But in general, we can hear between 20 hertz and 20,000 hertz. That is known as the audible range. Anything below that range, so less than 20 hertz, is called infrasonic. Anything above 20 kilohertz or 20,000 hertz is ultrasonic. Of note, this scale cuts off at about 1 gigahertz. It cuts off about 1 gigahertz because this, what it is air molecules bouncing back and forth relative to each other. If you vibrate them at a frequency higher than 1 gigahertz, what happens is the air literally rips itself apart. That everything's vibrating so fast that the atoms just shred themselves. And you don't get sound, you get an atom shredding itself. So basically a nuclear explosion. You know, kind of the same as sound, really. Yeah, 1 gigahertz breaks it down. Now, these 3 different areas are kind of interesting. What I'm going to do is I'm going to start with infrasonic, spend a long time on audible, and get to ultrasonic. And I don't have much to say about infrasonic, other than they have some really cool effects. Infrasonic waves are very common in nature. Weather patterns cause infrasonic waves. Earthquakes, right before an earthquake happens, there is normally infrasonic waves put out. The same for tornadoes and most storms. That if a storm is approaching, the storm coming will produce infrasonic waves that will slowly travel. A kind of interesting thing is there was this old one of those like farmer's wisdom things that like when the cows start acting a certain way, a storm is coming, and it was like a known thing. Like the cows start freaking out, a storm is coming. It's actually a real thing. Cows, other cattle, and elephants randomly have the ability to hear infrasonic waves. And so when a storm is approaching, a cow can hear it. And like cows with excluding like I looked at the weather channel and looked at the weather online, a cow will know when bad weather is happening before a human will because they can literally hear it coming. And a lot of our tornado detection system type stuff, it's just detecting infrasonic waves, seeing what we can hear. Okay. Now, in the audible range, as I said, we can hear everything from about 20 hertz to about 20,000 hertz. And how we hear is actually incredibly complicated. And it's not just simple O waves. How loud something is, like if it's quiet or is it loud, that idea. You'd like to think it's just the amplitude of the wave, but it's not. It's much more complicated. It's related to the energy of the wave, but the thing is we can't hear all frequencies the same. These two tuning forks, when I hit them, this this little one sounded a lot louder, at least to me. I don't know how it sounds to you guys. They're actually the same volume. It's just the high-pitched one we perceive louder. That we perceive high-pitched frequencies as louder than low-pitched frequencies. That something with a deeper, lower pitch, lower frequency will not seem as loud as something high-pitched with a high frequency. What we can measure is what is called the intensity, which the intensity uses the symbol capital I. And you know what? I'm going to change the font of that capital I there real fast so that you can tell it's not a L. Uses the symbol capital I. And it's just how much sound energy per area hits something. That is how we can measure how loud something is. See, before when I showed this GIF of how sound waves work, this is kind of a little bit of a stretch that what happens. Sound is not very directional unless you put a shit ton of effort. When I speak, the sound waves leave my mouth in a cone in all directions. And if something makes noise, what's happened is the sound waves lead it as a sphere going out. If I look at this picture, this is a in the bottom right. This is a 2D picture version of a sound wave happening. And what happens is the sound wave is going to spread out into bigger and bigger radius as it goes. But really should be a sphere going bigger and bigger in each direction. What that means is the energy of the wave is going to dissipate as it goes. That the further away you are from something making noise, the quieter it seems. And the reason why is the energy is spread out. In fact, the intensity goes as 1 over the radius squared. Because as you get further and further out, the surface area of the sphere, for lack of a better term, is going to go by radius squared. And so if you hear something and you move twice as far away, it'll be 1/4 the volume. You move 3 times away, it'll be 1/9 the volume. That's why you can't hear things far away very well. It's because the sound wave isn't just coming at you, it's spreading out. And as it's spreading out, it's getting diluted over a large area. Does that make sense? Now, in the audible range, we have a minimum frequency we can hear, once again. But we also have a minimum volume. Once again, is different for people. Because I can stay at I can go for the same frequency. And as this thing goes, it'll slowly die down. And if it gets quieter and quieter, I don't know if you can still hear it, I can. It'll just become quieter and quieter, even though the frequency hasn't changed. What happens is there is a minimum sound intensity our ears can pick up. It is approximately 10 to the negative 12 watts per meter squared. This is known as the threshold of hearing. And of note, 1 watt per meter squared is painful to hear and would actually cause damage if you hear it because it is so loud that the vibrations would be so much our ears can't handle it. This is separate from frequency. Now, because we're going from something of 10 to the negative 12 to 10 to the 0th, that's a huge scale of numbers. Sound intensity level. sound intensity level is normally measured on a logarithmic scale or the decibel scale. And what we'll say is the intensity of sound is measured in watt per meter squared, but the intensity level will be a decibel, where a decibel is just going to be the log base 10 of the intensity. It's a way to talk about how loud something is on a relative scale. Now, of note, it's not a bell, but a decibel. So the bell being named after Alexander Graham Bell. He made the phone and did a lot of other things with sound. Deci is one of our metric prefixes from way back in chapter 1. 1 decibel is just 1/10 of a bell. No one ever uses bells though, so you could ignore it. And what it is as society, we define 0 decibel as the threshold of hearing. That 3 decibel is so quiet you probably can barely hear it. And since it's a logarithmic scale, that means anytime something becomes twice as loud, that means you add 3 decibels. Now this seems weird. 63 decibels is twice as loud as 60 decibels. Like that doesn't seem to make sense, but once again, it's a log scale. It is a base 10 log. And so when we talk about how loud something is, we'll just put it in a decibel scale, where a whisper is 30 decibels, rain is 50, a dishwasher is 60, a food mixer is 70, and so on. Now, of note, anything higher than 80 decibels can do permanent damage if you listen to it for a long period of time. How long would depend on the decibels. So from 85 to 120 decibels, it has a time limit of how long you can hear it before permanently damaging your ears. This is why, like, if you're using a chainsaw, people always make a big deal you got to wear ear protection. That's because chainsaw is about 110 decibels, and if you have that noise in your ear for longer than 2 minutes, it can do permanent damage. Of note, once you hit 120 decibels, it can instantly do permanent damage to you if you hear it. Now, these things are assuming you're right up against it. Keep in mind the intensity level goes down with distance. So when I say an ambulance siren is 130 decibel, I mean you have your ear up against the ambulance siren. If you have an ambulance driving down the road, it would no longer be 130 decibel because it's spread out as it moved further away. Does that make sense? Now, every time you bring decibels up by a factor of 10, what you're doing is you're increasing it by a certain amount. Let's say you up the volume of something 20 decibels. When you up the volume of something 20 decibels, that means it's 100 times louder. If you up the volume of something 40 decibels, that means it's 10,000 times louder. How to work decibels is if I ever tell you we have an increase in volume of some number of decibels, divide by 10. So if I say we have an increase of volume of 30 decibels, I'll say, okay, 3, and just do 10 to that number. Something that is 30 decibels louder, the intensity is 10 to the third times louder. You can also go the other way. If I tell you something goes, I'm just putting a random number of zeros. Sure, that's good. If I tell you something is 1,000,000 times louder, and like we increase the volume, it's 1,000,000 times louder. Well, 1,000,000 is 10 to the 6th. If you make something 1,000,000 times louder, that is an increase of 60 decibels. Because I just took my 6 and multiplied by 10. That's how sound works. And if you say that something is at 40 decibels, 40 decibels means it is 10 to the 4th or 10,000 times louder than the threshold of hearing. Any questions here? This is always one of the things that people usually have a hard time with. So I would want to make sure you understand. Any questions? Now, decibels is a set value. When you have a speaker, you can say how many decibels is coming out. Normally, as I said, that's just going to be If you do a log base 10, how many times the limit of hearing? Like I know um, my amp downstairs for my TV, like I normally have it set to like the volume has numbers. It says like 36. Well, let's just say I set it to 30. If I set it to 30, I mean that means the intensity is 1,000 times the limit of hearing. If I set it to 40, it's 10,000 times the limit of hearing. But when you set something to a set amount of decibels, some people may think it's loud, some people might not think it's that loud. Decibels is a set thing, but how loud something actually is going to vary from person to person. And also, once again, we pick up better frequencies better than others. A low frequency at 30 decibels will sound quieter to you than a high pitch frequency at the same level of decibels. This is just because the nature of how our hearing works. Okay? Now, this was all for the audible hearing. Let's talk about what happens when you go past that. Higher pitch than we can hear is called ultrasonic. And ultrasonic waves are just above what we can hear. A lot of animals can still hear them. This is how bats and dolphins, and because it makes me laugh, Daredevil, how they operate. Bats aren't actually blind, for the record, but what they can do is they can put out high-pitched ultrasonic noises. And the high-pitched ultrasonic noise will spread out and it will bounce against things they hear. And they'll just listen for the echo. That's why it's called echolocation. You're listening for the echo. And you're just shooting noise at it and seeing what comes off. And with that, you can tell where something is and if it's moving. Is it moving towards you or away from you? That idea of it's moving towards you or away from you, keep that in mind. We're going to talk about that in like 3 slides, something called the Doppler effect. But we'll come back to how they can tell that. But same idea with dolphins. They make a high-pitched ultrasonic noise and they listen to the echo of what it bounces off. Ultrasonic works very well for this because with the high frequency, it's much easier to detect. We also use ultrasonic in medical ideas. So X-rays is a type of electromagnetic radiation. And if you take an X-ray of something, it can it has a lot of energy and it can harm living tissue. X-ray is really good for looking at bones, but you can't look at your liver or your bladder or a newborn child, like in the picture below, because it has a lot of energy and can do damage. Ultrasonic waves can pass through some living tissue and bounce off others. And what an ultrasound is, also known as an echogram, is you shoot noise at something, ultrasonic noise, and you see what the sound waves bounce off of and what they go through. And so this echogram of a child, where this is the head over here and then the body over here, what it is just it's bouncing off the bones of the child, where we are literally looking at hunks of skull, spine, a hand, and like thigh, and apparently a tail. I don't know what this is. Um, maybe the other arm, probably the other hand. That would make sense. I don't know. I don't actually know this shit. I don't have kids. Um, but what it is you're just putting a high frequency noise out and seeing what it bounces off of. Okay. Now, how fast speed sounds? How fast speed sounds? Yeah. How fast speed travels? There we go. Is going to be based off the material. The speed of sound is changes with temperature and what the material is. That the hotter something is, the faster sound travels. But in 20 degrees Celsius, which is about room temperature, it's about 68-ish Fahrenheit, speed travels at 344 meters per second. This is much slower than the speed of light, where light travels at 3 times 10 to the 8th meters per second. This is the idea that when fireworks goes off, you can see it and then hear it, or same thing with lightning. You see it, then hear it. It's because the light will travel towards you much, 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 much quicker than the sound will travel towards you. In fact, if you're looking at lightning or fireworks or anything, if you count how many seconds in between you see it and hear it, you can normally get a pretty good estimate of how far away it is. Because sound will travel at a set speed, light will travel at a set speed. It's just light moves faster. Okay. Okay. Questions there before I make this get weird. Okay. So, the Doppler effect. I don't know if what I'm about to do is going to work. You're going to have to tell me. When I make this go at a set frequency, what happened is this frequency, 426.6 hertz, is moving through the air. But if I start moving this around rapidly, let's give myself some more space. As I said, I don't know if it's working through the headphones or not. I'm hoping. But what if I start moving around rapidly, the frequency will seem to change a little bit. That it won't seem constant. It'll seem like it's kind of wavering a little bit. See if this one works better, because that didn't pick up well for me. That's working better for me. Is that sounding like it's wobbling a little bit when I do that for you guys?
Yeah.
Cool. Nice to know something I do works. This is known as the Doppler effect. It was first noticed in 1842 by a man named Johann Christian Doppler. And okay, this is one of the favorite things I have and like weird shit people do in science. Johann Christian Doppler like theorized it, and it was first tested by a man named Christopher Henrik Diedrich. That what he did, um, oh, Christopher Henrik Diedrich buys ballot. It's a long name. He no, that buys ballot. I gotta check that. That name might be wrong. I don't think that buys ballot is part of his name. I think that just got a copy and pasted in there for somehow. What he did is he had a train and got a horn section of an orchestra to sit in the train car. And then the train go by and he had people sit there and listen to the horn section play a set note and see what they heard. Which I just think is hilarious that like a train and an orchestra driving by is how they work this out. But here's the idea. Frequency will have a very set sound when it's stationary. If something producing a set frequency is moving, someone listening to it will hear a different frequency. This is why when a car drives past you, you hear like a that it seems to go up and then down. Same like an ambulance or police siren drives towards you or past you. Is the frequency doesn't seem constant. It seems like it goes up then back down. The reason why is because if you are stationary, you're sending out sound waves in all directions. And that when I hit these tuning forks, the tuning fork is just sending sound waves out. But if you look, let's look at this GIF at the bottom. Right here, I don't know if nope, I can't pause it really. When the car wasn't moving, the sound waves were equally moving out. But if the car starts moving forward, what it starts to do is it starts catching up to its own sound waves. And then it gets closer. The sound waves appear closer because let's say it's making sound waves going out, out, out. If I make a sound wave and then keep catching up to it, when I make the next sound wave, I'll be closer together. This picture, I think, shows it well. That the sound waves coming from this motorcycle, if it was stationary, would be nice, uniform, concentric circles making their way outwards. But because this is moving to that way, it's catching up to its own sound. And the waves in front of it get bunched up. And the waves behind it seem further apart. And what that means is when the motorcycle goes towards you, the frequency goes up. When the motorcycle goes away from you, the frequency goes down. And that's the Doppler effect. That anytime something is making noise, no matter what its frequency is, if you and the thing are getting closer together, it will appear to have a higher frequency than it really does. And anytime something you and something making noise and moving further apart, it'll appear to have a lower frequency than it really does. And so something rapidly coming at you will get a higher frequency than it has in real life. Something moving away from you, a lower frequency. It's just because you're getting the waves quicker. Making sense so far? Now, this gets crazy when you start going real fast. So, let's say we got somebody not moving. Bottom left picture, right? The waves come out uniformly. Anyone absorbing at any point hears the same frequency. Then they start moving. If they start moving, what's going to happen is the waves bunch up. Because once again, it's going to be as you're moving, you put out a wave, you put out a wave, you put out a wave. And if you're catching up to putting out your waves. But what's going to happen is if you hit the speed of sound, you're going to make a sound wave. But if you're traveling at the speed of sound, you're going to get to a listener the same time the sound does. And things, the waves are like, we view them as, coming back and forth, but really it's going to be a continuous thing. And if you're traveling at the speed of sound, what happens is Mhm. if I travel from here to here, and if I'm moving the speed of sound, I'm probably have a pretty good engine going. So let's say I got a plane making a lot of noise, right? What's going to happen is the plane will make some noise here, and then 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 some noise here, and really be continuously. And if someone's just sitting at the end listening, what's going to happen is all of the noise I made of this entire path is going to reach that person at the same time. Because what's going to happen is the entire noise of the trip, it's the noise I made, uh, the noise I made at this moment is going to get there the same time as me. But the noise I made at this moment is going to get there the same time as me, and so on. And when you start traveling the speed of sound, is that all of the noise waves get grouped together. And if you go faster than the speed of sound, called supersonic, what you do is you create a V-shaped bell wave, where that's going to be where the sound hits. And what it is that when I travel the length of this black line from here to there, the noise of that entire trip, from that entire trip, will hit a observer at a set spot, where right here, right here, right here, and so on will be a wave of noise, a wave of noise that travels with you. And that wave of noise will be the entire trip's worth of noise at once. And what happens when something moves at the speed of sound is that the idea of when something passes the speed of sound, there's a sonic boom. And you probably heard that idea. That when something goes at the speed of sound, there's a sonic boom, there's a loud noise. There is no just instant sonic boom. When something moves in the speed of faster than the speed of sound, there is a constant wave of noise. That is all of the noise of the trip moving with them in a set cone. And what it is when something goes near you faster than the speed of sound, when that cone passes you, you hear a long trip's worth of noise at once. It sounds like a large boom because it's a cacophony of noise from a long time period at one moment. But you hit the speed of sound, there's a sonic boom, it's done. The sonic boom is a continuous ongoing thing. It's just only someone stationary hears at a very set moment when that cone passes you. In fact, the person in the plane would never hear it because they're moving with the plane. And so they don't have to worry about it. Now, I'm going to use a few technical terms in here. Well, not too technical, but a little technical. So I just want to make sure we're on the same page. I'm going to talk about things in terms of Mach a little bit. Mach 1 is the speed of sound. Mach 2 is twice the speed of sound. Mach 3 is 3 times the speed of sound, and so on. It's named after Ernest Mach, who studied this stuff. What happens when a plane flies past you at Mach 1 or faster? Is that the nose of the plane will make a traveling shock wave. That when that shock wave passes you, you hear all of the noise. And actually, for a plane, there's actually two booms you hear because the tail of the plane makes a second shock wave that all the noise from the trip you hear then too. The thing is normally you only really hear one because they'll be so close together in time that you won't notice the difference. But here's the cool thing. This wave of noise, if you fly very close to the ocean, this wave of noise can grab and hold moisture. In a plane flying near the ocean, you can actually see the sonic boom coming. This wave of water will just be grabbed and held on. Bullets also pass the speed of sound. This picture to the right is showing the sound waves coming off a bullet. And you can see this front line. That would be this sonic boom coming. And in this bottom bit, this is a plane traveling real fast in a marina, which I assume pissed off just about everyone. But you can see it building, catching the water and building this cone of noise, which shows it's still in the upper left. And if I'm talking about sonic booms, I just have to include Guile because I'm a nerd like that. Questions though? Now, this idea that if something is, where's my camera? There it is. If something is moving, making sound while moving forward, the sound compresses. And if something is making noise while moving apart, the sound goes further apart. The Doppler effect. That is true for sound waves. But here's the thing. That'll work for any other type of wave. And if you are shining a light and you're moving quickly in the direction of the light, it's still a wave that can be compressed. That whole E field, B field thing. If I start moving in the direction the light is shining, I can still compress it. The Doppler effect also exists in electromagnetic waves. And that you can actually solve if you fire something with a set frequency. And I would say electromagnetic wave with a set frequency, which could be visible light, but could also be radar, which is a type of electromagnetic wave, or FM radio, or TV, or those are all radio waves. Radar, FM, TV, shortwave, AM, those are all radio waves. What happens is the velocity of something relative to the source watching will get shifted. That something might look like it had a color shift. It might look slightly different if it's moving away from you or towards you very quickly. For this reason, people often talk about things having a red shift or a blue shift. Anytime something is moving away from you, you can say it has a red shift. What that means is it'll appear more red if it was visible. It'll appear more red because if it's moving away from you, the frequency goes down. If the frequency goes down, the wavelength goes up, and red is the highest wavelength we can see. Likewise, something moving towards you, we say has a blue shift, because if it's moving towards you, it'll appear more blue than it really is. That's because when it moves towards you, its frequency goes up. High frequency means low wavelength, and blue is the lowest wavelength you can see. And so something moving quickly towards you looks more, or if you're moving quickly towards something, same idea, will look more blue. Something moving quickly away from you will look more red. Astronomers use this because they use it to figure out the speed or the relative speed of other celestial bodies. You see, we know what color a star should be based off its temperature and a few other quantities. And we can look at a star and say it should be this color. Is it more red? Is it more blue? And based on is it more red, is it more blue, we can see if it's moving away from us or towards us. And actually, mathematically, we can solve for it exactly what speed. It's commonly used for big bodies because we look at the left side and the right side because if it's rotating, they'll be slightly different, but that gets a little complicated. A little close to home, that's how Doppler radar works. If a cop is going to measure your speed and they have a radar gun, what they do is they basically fire a laser. It used to be radio waves, but the more common ones are lasers now, and they fire a laser at your license plate. The light goes, and the thing knows exactly the frequency that it's firing. It hits your license plate and bounces back. It measures the difference in frequency of what it emitted and what bounces back. And by measuring the difference in the frequency of what it emits and what bounces back, it can calculate the speed of the call. Doppler radar in the terms of storms is the same thing. We fire radio waves at a storm, we see what bounces back. Actually, probably in ultrasonic waves at a storm, might not be electromagnetic. And we measure what's the change in frequency. If we know the change in frequency, we know the change in speed. But it's a general idea. Sound waves can get messed up when you move towards, or sound waves or light waves can get messed up when you move towards or away from something. Any questions though? So that's the end of this chapter with my out-of-tune ukulele. So I'm going to stop there. Homework for chapter 5 is due tonight. Tonight being the 17th. Midterm grades are also due tonight, but they'll due before they're due at 5 o'clock and your homework's due at 11. So I already entered the midterm grades because I can't, it would be too late if I wait to this homework. So midterm grades are up. So if you want to see those, go check them out wherever you have to check them out. And I'll see you next week.